topic for today is this. So let's assume that we're in the case where we're going to do a confidence interval from U. But we haven't collected the data yet. Can't read that very well, can you?
Well, my eyes are going back.
Try it again. Really? Maybe my handwriting's so bad that I had to focus 3 or 4 times. You guys read that?
Yep.
So the situation we're in today is we know we're going to do a confidence interval from U next week or at some point, but we haven't collected our data yet. And the question is this, or the problem or the issue is, all right, so we're going to collect some data, we're going to do a confidence interval from U. What if it turns out that our confidence interval is enormous? It's huge. So like, let's just say, for example, that we're interested in the true average height for Casper College students. So the actual true average height for Casper College students. So if we took a census, we'd have to, measure every single person's height on campus, which is either difficult or impossible to do. So we say, all right, we're going to take a sample. And then we're going to get a confidence interval for that average. Well, what if we take our sample and it comes back that our confidence interval goes from 4.5 feet to 7.5 feet. We think the average height of Casper College students is somewhere between 4.5 feet and 7.5 feet. Is it true?
Yeah.
I bet it probably is. Is that very useful? Is that very informative? Not at all, right? Doesn't really help you much at all. And so, what's the problem with what we had there, that circumstance? Well, the margin of error was too big, right? We had some point estimate, and then we had a huge margin of error this way and a huge margin of error this way. So if the margin of error is too big, it doesn't help you. It's not informative, right? So the question today is, how large of a sample do we need? So this is the question. How large of a sample do we need to get some margin? Like we say, okay, this problem with the average height of Casper College students. You know what? If the margin of error is 1.5 inches, I'm good with that. Right? So if the margin of error is 1.5 inches, that means our point estimate's here. We go 1.5 inches this way, 1.5 inches this way. So what's the total width of the confidence interval?
3 inches.
Be 3 inches, right? So we say if our confidence interval is 3 inches wide, I'm okay with that. I think that's going to be useful. And so the question is, how many observations do you need to make that happen? Do you need to measure 10 student heights, 50 student heights, 100 student heights? So that's the question we're going to address today. Okay, so remember, the stuff we're doing right now, this one and then the next topic, we've not taken a sample yet. We can't get a confidence interval because we don't have the data. What we're attempting to do is figure out what sample size do we need in order to get a certain margin of error. Do you see how this is a different approach or different topic than what we did before? Okay. So, if you do a confidence interval from U, right, it's going to be x bar plus or minus. Now, it depends if it's a z or t, right? But either way, you're going to have a critical value times the standard deviation divided by the square root of n. So this is what your confidence interval is going to look like. Now we know if it's a z, this is going to be a z critical value, and this will be sigma. If it's a t interval, you're going to do this would be a t critical value, and this would be s. So one way or the other, it's basically that. Which portion of that is the margin of error?
The CV times.
That's the second then.
Yeah, it's the stuff that gets added and subtracted, right? This entire thing here is the margin of error. Okay. So we're trying to figure out what sample size we need, right? If you're going to use a t-critical value, I'm going to argue that we should probably just, since this is just kind of a ballpark approximation anyway, probably we can't plug in a t-critical value here. Why?
Because we're going both ranges.
Well, what do you have to know in order to, so you take your table out and you want to pick a t-critical value, what do you have to know?
Sigma.
You have to know, no.
No.
For a t-critical value, you pick the degrees of freedom, right? What's the degrees of freedom based on?
Oh.
Sample size, but we don't know the sample size yet. So what we're going to do, let's just pretend that we know, so we're going to have a sigma here and a z-critical value here, just because we're kind of doing a ballpark approximation. It's not a perfect science, it's just going to give us an idea of how big of a sample that we need. So let's do this. Let's say that I'm going to write down an equation here. I'm going to write down the margin of error is equal to a z-critical value, some number off your z table, like 1.96 or something. And so we're just going to do z right now, times sigma over the square root of n. So if you ended up doing a z interval, this would be true, right? We'd say the margin of error is equal to z critical value times sigma over root n. So what we're going to do is solve this equation for n. Just do a little algebra, right? So I've got a z critical value in sigma, so I can divide both sides by those. Get rid of that on the right. So get that. And then you can kind of think about doing this in a number of ways, but you end up with the square root of n is equal to the z critical value times sigma divided by the margin of error. And if I want to solve for n, how do I get rid of, what's the opposite of square rooting something?
Square.
Square it, right? So I'll square both sides. You square both sides and you end up with this. So this is the formula we're going to use to get a ballpark approximation of the sample we need. So this said, I forgot it was squared, right? There we go, squared. The margin of error, remember you get to specify that. You get to pick what you want as your margin of error if you're going to do your confidence interval. The z critical value, where's that going to come from? Let's get the z table. Like you say, okay, well I'm going to do a 95% interval, z, so it's 1.96 or something, whatever. The only thing we don't know is sigma, right? We don't know what sigma is. And so that's kind of the crux of the issue. You have to have some sort of an estimate for sigma. So I kind of skipped this slide, but this basically says the same stuff that I mentioned on other stuff. So basically the question is today, how many observations do we need so we get the desired precision? When we say precision, that just means margin of error. You have a margin of error that's a certain size. So this is the formula. And notice this is the same thing I have not two slides ago, but 2 pages ago. The only difference is what? Instead of sigma here, I have sigma EST. Okay? We can't just plug in S. Why can't we just plug in S? We don't have a sample yet. If you don't have a sample, you can't get S. Okay? So we have to estimate sigma in some way, shape, or form. The z critical value and the margin of error are super easy to get. You know the margin of error, you get to choose it, the z critical value just comes off your table. The thing that's going to be the big issue is the sigma EST. to get sigma EST, there are a number of ways that people do this, and like I said, it's pretty important. If you're going to do this confidence interval and you want your margin of error to be about what you think it's going to be, this is going to be pretty important. You could use an educated guess. So, if you've worked with this type of, let's say you're a educational psychologist and you work with third graders and reading levels and things, maybe you've collected a lot of data, worked with data over the years, you actually have a pretty educated guess as to what sigma is. You can use it. I would say err on the side of choosing a sigma that's a little bit bigger maybe than you think, but yeah, go ahead and use it if you've got an educated guess. Maybe somebody else has done research in this area, so you can just kind of do a lit review and look and see what they've used or see what they got out of their sample or something like that. And, maybe you would expect your group to be somewhat similar in terms of standard deviation. You could use a pilot study. You guys know what a pilot study means? A pilot study would be, all right, so let's say you're working with third graders and you want to get a confidence interval for some reading level or achievement or score or something like that. What you could do is, knowing that you're going to have a big sample at the end of the day, you could take a smaller sample to start out with and look at what the standard deviation is from that smaller sample and use that to figure out how many more you would need from your big one. So a pilot sample, a pilot study is a smaller sample you take at the beginning to help you determine how many more you would need after that. So that's a smart idea. If you really have no idea, a pilot study might be a good way to go. The range method, to get sigma EST via the range method, what you do is this. You take the largest value you think you might see, minus the smallest value you think you might see. And before I tell you what we're going to divide by, remember the empirical rule? Right, the empirical rule said that if you've got bell-shaped data, if you've got normal data, 68% are within one standard deviation. If you go 2 standard deviations, what percent do you get? That's 95, right? And then if you go 3 standard deviations, you get what? 99.7. That's percent. So according to the empirical rule, we get something like this. Now, do we always know the empirical rule applies? No, not really. But just to kind of give us a ballpark estimate of what sigma might be. If we take the biggest value that we might get, and we take the smallest value that we would get, we take that difference, so we get the difference from here to here, and we divide by 6, right? Because there's 1, 2, 3, 4, 5, 6 kind of units of standard deviations there. If we take the max value minus the min value that we think we might see, and then we divide by 6, that gives us kind of a ballpark estimate of what sigma might be. Do you see how that might work in some cases? In some cases, maybe it would give you a horrible estimate, but the justification is literally just kind of what I showed you there. Sometimes people use 4 instead of 6, right? Why would they use 4? Well, if you go back to this, well, maybe the max value might be, here. Maybe you think it's going to be about 2 standard deviations each way. And so if you go 2 standard deviations this way, 2 standard deviations, that's 4 there. That's where the 4 comes from. So people sometimes, with the range method, will use 4. But I think in the homework and things like that, I think 6. So all you do is take the largest value you think you might see minus the smallest value you think you might see, divide by 6. There's no most conservative choice for sigma, sigma EST. What I can't exactly explain what I mean by that, but once we do the next little section, that'll make sense.
So we kind of do like a sigma claim, in a way.
It's not really a sigma claim. I guess it could be, if you could use a sigma claim as your sigma EST if somebody knows what they're talking about. Let me show you with an example of what I mean here. So the kind of things that people do is something like this. Let's go with that example that I mentioned a moment ago. So let's say that we want to get a confidence interval for the true average height for CC students. And what did we say a usable, reasonable margin of error might be? Did we say 1.5 inches? Okay, so let's say we want the margin of error to be 1.5 inches. Okay. What do we think we should use for sigma EST? I don't know. I don't know what the standard deviation of heights of CC students is. But couldn't we maybe use the range method? We could try. So the range method, we take the largest value that we think we might see minus the smallest value that we think we could see in this population and divide by 6. So what's the largest, tallest person we could ever possibly draw?
8 foot maybe.
I don't know if there's any 8-foot tall CC students.
7.
Yeah, maybe we've got a basketball team, right? So maybe there'd be some years, I don't know what the tallest basketball player is this year, but probably, you're probably not going to see anybody,
Over 7.
you're definitely probably not going to see anybody taller than 7 feet, although I guess maybe you could. 6'10", 7 feet. Again, this is just going to be a ballpark number, so let's say 7 feet, just to make a round number. Minus, all right, what's the shortest student that we could see? 4 feet? I don't know. Is there anybody shorter than 4 feet? I don't think so, right? Maybe say 4.5, 5. I don't know. 4.5, sure. 4.6. Let's make it so 4.5. And we're going to divide by 6, right? Now we want this in inches. So if you go 7 feet, that's 2.5 feet, right? If you take 7 feet minus 4.6, it's 2.5 feet. So what's that, 30 inches? 30 inches is 2.5 feet. So 30 divided by 6 is 5 inches. Do we know that's right? No, but maybe it's just going to, and if you're ever going to, you want to err on the side of having that sigma a little bit bigger rather than too small. So yeah, maybe that's going to be a reasonable number here. So the game that people would play would be this. We'd say, all right, so the Z critical value, let's say we're going to do a 95% confidence interval. If I'm going to end up doing a 95% confidence interval, what number would I choose for the Z critical value? 1.96. The sigma EST, we said that was going to be 5. And the margin of error, we chose to be 1.5. So all you would do is take your calculator and work out what that is. So we'll take 1.96 times 5 divided by 1.5 and we'll square that. So 42.68. You can't take fractional parts of people observations, so you always want to round up for these. Never round down, you would always want to round up. So the answer you would give here would be 43. Okay? So the answer you'd give here would be 43. Let's say, you know what? I don't have the energy to get us, and time and resources to get a sample of 43 people. Let's take a simple random sample and measure all 43 people. So what would you change? What would you go back and say, well, this is too much? Would you want to change this? Would you want to change your Z critical value? No. No, once you choose that, that should stay what it is. You say, I'm going to do 95%, you leave it at that. Would you change your sigma EST?
Yes. No.
Probably not. If you think that's what it is, you should leave it there. You shouldn't probably change that. But you change your margin of error, right? Because you get to choose that. So maybe you say, all right, well, maybe I can't get an inch and a half, but maybe I'll get 2. So then you would repeat the same thing, except you would put 1.96 times 5 divided by 2. And that's 24.01. So you round that up, and it would be 25. Okay, you see how this works? You get to pick and change the margin of error. If you, the researchers, say, I want to have an inch and a half margin of error, or 2, or 1.3, or whatever you want, you get to pick that. And you get to kind of adjust it and play around until you get a balance of margin of error and sample size. Does that make sense? Yeah, so maybe you say, all right, well, I can live with 25. The other thing that you probably want to do is realize if you don't know what, if you didn't know what sigma was, then what kind of interval are you going to end up doing at the end of the day? If you don't know sigma, you'll do a t interval. If you don't know sigma, you do a t interval. And the t critical values, are the t critical values bigger or smaller than the z? You can look at your table, or the t are bigger, aren't they? So go in that column from 95%. The z's 1.96. All the t's are bigger than that, at least by a little bit. The bigger the sample size is, the closer they are. But if you've got a small sample size, they could be pretty close. So sometimes what people will do is they'll say, okay, this was 25, but I'm going to bump this up just a little bit because I know at the end of the day I'm going to use a t critical value which is going to be bigger. So sometimes people say you should add 10% to this or something like that, just to be kind of on the safe side. For class, for the exam, whatever, just round up and give me the answer. So if it's 24.01, round up to 25. Call it good. But just realize in practice people might go a little bit higher than that to account for the fact that they'll end up using a t critical value. Okay. So a researcher wants to estimate the length, should be average. The average length of commute for workers at his company to within 1.5 miles with 99% confidence. How large of a sample does he need if he thinks the longest commute is 22 and the shortest is 2? So the first thing you would do is you say, all right, well, it's n is equal to the z critical value, 99%. That's 2.5758. Oops. That's a 5. Divided by the margin of error. The margin of error is 1.5 miles. Oh wait, we don't know sigma EST. We've got no basis to do this, right?
We should just do the range.
We could probably use the range method here. It's not going to be perfect, but maybe it gives us at least a reasonable guess. So sigma EST, we take the max, so 22, minus the min, which is 2, and we divide by 6, right? So 20 over 6. So that's 3.3 repeating.
We round up to 4.
You can just leave it as 3.333 or something. Or you can round it up if you want to be a little more conservative, just round it up to 3.5 or something like that.
Okay.
In practice, you might do something like that. So I just put in the 3.333 right there, and now we can just plug our calculator. So I get 32.76. And what would I do with that number? Round it up to 33. So we'd say 33, and realize that at the end of the day, we'd end up using a t critical value, so we may want to even give ourselves a little more cushion than that. But 33 might be a good place to start. What about number 2? It says, how large a sample does he need if he thinks the standard deviation is 4? Yeah, just do the same thing, except put in 4 for sigma EST. 4.61 or something like that. And remember, even if it's, no matter where it is, you always round, which way? Up, so we round to 5 here. And so the moral of the story is you say, okay, well, is that right? Oh, that's not right. Yeah, that's not right. Let me redo that. I typed it in the calculator wrong. It's like 4. That's not a very good example at all. Let's try this again. I changed the wrong number. So 47.18. Does that sound better? All right. So 47.18 is what you get when you actually type this into the calculator. And which way do I round that? Round it up to 48. Yeah, with a bigger sigma EST, you should get a bigger, there's more uncertainty, so we need a bigger sample. Okay. Any questions on this?